IP version 4, which you'll commonly see written as IPv4, is the primary protocol for almost everything that we do on today's networks. If you're communicating between two different devices, IP addresses will be used on both of those devices. There's a newer version of IP called IP version 6 or IPv6, and you'll find that most major operating systems now support both IPv4 and IPv6 on those systems. These are the IP addresses on my device. I have both IPv4 addresses and IPv6 addresses that have been assigned to my computer. This means that I can communicate to any other device on the internet, either using IPv4 addresses or IPv6. IPv4 addresses are 4 separate numbers, all separated with a period. So an example of an IPv4 address would be 192.168.1.131. We can also view this in a binary form. You can see there are 32 total bits in an IPv4 address, and they're separated into these 4 different blocks. This is the binary representation of 192. This is the binary representation of 168, and so on. You'll sometimes hear these referred to as 8-bit segments, 1 byte, or 1 octet. And having 4 of those together is 32 total bits or 4 bytes of an IPv4 address. If you were to convert this binary value back to decimal, you would see that 11000000 is 192. This also means if we have 8 of these bits and they're all set to 1, the maximum value would be 255. So any of these groups or octets can have a maximum value of 255. We quickly realized with the popularity of the internet that we were going to exceed the capacity of what IPv4 addresses could provide. So we created IPv6, which was a new form of IP that had a much larger address. You can see that an IPv6 address is 128 bits in length. This means that you can have a very large number of total addresses, which ultimately means that the 6.8 billion people on Earth could have a very large number of addresses for each individual person. This gives us enough addresses to assign an IPv6 address to almost anything that we might use. You can see that IPv6 addresses are separated into 8 different groups, and each one of those groups consists of 16 bits. This is also 2 bytes or 2 octets. Instead of displaying these addresses as binary or decimal, you can see that in IPv6, we choose to address these in hexadecimal format. So a common IPv6 address might be FE80:5D18:652:CFFD:8F52. As you can tell, it's a much larger address, and in some ways, it's a much more difficult address to try to memorize. For that reason, your DNS is going to be a very important tool to use on your network because you'll very often be referring to these servers by their name instead of their very long and relatively complicated IPv6 address. We also tend to see IPv6 addresses assigned with a 64-bit subnet mask. That means that the first 64 bits are the network address, and the last 64 bits are the host address. If you're assigning an IP address to a device, there are a number of important configuration parameters you need to add. The first would obviously be the IP address itself. So for IPv4, you might assign it an IP address of 192.168.1.165. Every device on your network needs a unique IP address, so you have to make sure there are no duplicates when you start assigning these IP addresses to devices. Along with the IP address, we also need to assign a subnet mask. This will normally be assigned by the network administrator, and it's usually a format like this one, such as 255.255.255.0. Subnet masks are used by the local device to determine what subnet it happens to be a part of. So it uses this to mask out the IP address, leaving only the host address at the end. You'll often be provided both of these values at the same time. So if you're assigning an IP to a device, someone may tell you to assign 192.168.1.165 with a subnet mask of 255.255.255.0. If you only have one of these parameters, you won't be able to complete the IP address assignment. Both of these parameters are used in conjunction with each other, and you have to have both of them to assign an IP. If the device also needs to communicate outside of your local subnet, and most devices do, you'll need to also assign a default gateway. This is the IP address of a router that allows you to communicate outside of your local subnet. So the default gateway in this particular example is 192.168.1.1. In most cases, this is the bare minimum of configurations you would need to assign to a local device. So you would need an IP address, a subnet mask, and a default gateway. As I mentioned earlier, the domain name system server, or DNS server, is also an important component. We don't commonly type an IP address in the browser that we're using. Instead, we type www.professormesser.com or www.google.com. It would be very complicated if we had to remember all of these IP addresses and type them in manually every time we wanted to visit one of these websites. Instead, we have a service that does this for us. It converts between these names to an IP address. This is because the routers and other devices on our network don't know what these names mean, but they do know where to send your traffic if there's an IP address associated with it. So we need something that can translate between the fully qualified domain name, such as professormesser.com, to an IP address. And it's the DNS server that provides that translation. We would commonly configure a DNS in the IP settings of your operating system. So in my particular case, I've assigned 8.8.8.8. You'll also notice there are other DNS servers listed on my machine. That's because DNS is such a critical resource that it's very common to assign two separate DNS IP addresses to your configuration. That way, if one DNS is not available, you have another DNS that you can use. In my example, I have 8.8.8.8 and 8.8.4.4, both of which are DNS servers managed by Google.